Our next speaker is Britton Smith, who's already been mentioned a couple of times. His talk is entitled Ab Initio Simulations of the First Metal-Enriched Stars. Britton.
Thank you, Mike. I'd like to begin by thanking the organizers for letting me come in here today and speak about these results. I think they're very exciting. And I'd like to thank Raffaella for giving an excellent review. It set the stage for me very nicely. And before I move on, I'll also give a thumbs up to all my collaborators on this work, a couple of whom are here in the audience today, Mike Norman and John Wise, so feel free to talk to them as well if you want about these results. Just to review the review, here's what I think we know and what we don't know about forming the first low-mass stars, the first metal-enriched stars. We know that when you have some sort of cooling phase during collapse, you create conditions that allow fragmentation, but that fragmentation itself is a three-dimensional problem that seems to be very initial condition dependent. And so what we still don't know is that, we don't know the actual physical conditions of the first metal-enriched stars. What are the actual metallicities in these first clouds? What do their cloud structures look like, velocity-wise, thermal-wise? And we still don't really know, from simulations at least. From models we do, but we really don't have a good indication of where and how and when those metals get into the first star-forming gas. And that's exactly what we're trying to study in this work. So I think here's the recipe for what you need in order to study how metals get into star-forming gas for the first time in a 3D simulation. You, of course, need it to be cosmological with fairly high resolution. I think resolution of the order of what you need to simulate the first stars themselves. We have a resolution of about a solar mass per dark matter particle. You need to have radiation hydrodynamics to properly simulate the main sequence lifetime and supernova of the first stars, specifically the radiating phase, because these halos are very small and they efficiently blow out nearly all of the gas while the star is alive. So when we have the conditions of metal-free star formation in these simulations, we insert a star particle that represents a single 40 solar mass star that explodes with a regular core collapse supernova. We are also investigating other progenitors. I won't speak about them today, but you should feel free to ask me. And you, of course, need to follow the metal mixing, and you need very high spatial resolution. So we use the power of adaptive mesh to follow the collapse and metal mixing down to scales of roughly AU sizes. So the physics, of course, we have the radiation hydrodynamics, as well as the non-equilibrium primordial cooling with the tabulated metal cooling. It is simplistic and a rather crude dust model as well. I think these are areas where this could be improved. This is all done with the code called Grackle, which I will explain in a moment. And what we're simulating here is a fairly small 10 to the 7 solar mass halo that forms at redshift 10. And all we really do is run the simulation until something finally collapses with a metallicity greater than, say, 10 to the minus 6, roughly equivalent to the critical metallicity if you have dust. The code that we're using to do all of the chemistry is an open source code that was derived originally from Enzo's chemistry solver called Grackle. It does all the stuff that I talked about, and in a release coming probably within a few weeks, it will also include the radiative transfer fields and the atomic self-shielding in a public release. It is a library, not just a code that you copy and paste into your simulation code. It has APIs for C, C++, Fortran, and even a nice Python wrapper to run these calculations from a Python model. So if you do modeling as well as simulations, I think this can very help you. You can see the paper by Bhaskar Agarwal, who's also here today, that made use of this. So please ask him about his experience. It's very optimized. It's built for high resolution, large simulations, lots of cell updates per second. And it's community driven. There are a number of developers here in the audience today, including Simon Glover, who has been very studious in making sure that the chemistry rates are fully up to date. John Regan and John Wise. If you're interested, please have a look at grackle.readthedocs.io. So I'll begin by talking about the very first result that we had in this work. So we run the simulation. One POP3 star formed initially, and nothing really happened. What I'm showing you here is the density and temperature right in the region around the second POP3 star, which is going to form up here. And there is a secondary halo within just a couple hundred parsecs of it. And let's just see how it happens. I will also point out that you can get, at least right now, the last data set from this simulation at hub.yt. That's an actual web address. You can go there and load up this simulation data in an IPython notebook and have access to the YT analysis toolkit, and we will put additional data sets up there. So if you are interested in doing more with this data, we invite you to do so. Please do so. So here we go. The star forms, it shines, it blows out all its gas, and the supernova washes over this secondary halo. And the blast wave, combined with the virialization, kicks up turbulence that allows the metals to actually efficiently mix into the center of this halo in a period of about 25 million years after the star has formed, or actually after the supernova itself, right? And so we can see this process in action. Up here we have the metallicity as a function of radius from the central clump. And we see out here at scales of tens and hundreds of parsecs that there is gas at all metallicities from supersolar all the way down to metal-free. And as we get closer to the center, within a parsec, there is no unenriched gas anymore. And as we get closer and closer to the center, we've got eventually a knot that can collapse faster than the mixing timescale, and it runs away at that metallicity, which is roughly 2 × 10⁻⁵. You can see that all played out here. These are sort of the 3 relevant timescales of this process. We have the free fall time, the cooling time, and the mixing time, which I define as the inverse of the vorticity, the magnitude of the vorticity times a factor of 2 pi. It's the time that it takes to stir the pot once all the way around. And as you can sort of see in the bottom here, we compare the mixing and the cooling time scale to the dynamical time, and we see at large radii, the shortest time scale is in fact the mixing time scale, which is efficiently putting metals in faster than anything can run away and collapse, until we get to a scale just inside of about 1/10 of a parsec, where that mixing time scale becomes longer, and the cloud then finally runs away. So this is this external enrichment mechanism that we've been talking about, that we've heard about earlier. We've got this starless mini halo that gets promptly enriched in a time that is significantly less than the fallback time for these metals to fall back on its original halo, which would be something like 100 megayears. And this is star formation after a single supernova. So the stars that form here will directly trace their progenitors. Let's follow the collapse itself. Here we are, the same movie. Here's that density and metallicity. We can see that the metal blast wave came from that way and moved down, as we see less area here. So now I'm going to play this as we continue to collapse. We see we're at the mixing scale, where there's still a wide range of metallicities, and as we continue to zoom in, centering on the center of mass of this clump, the range of metallicities decreases further and further as we get to the center, where it's just almost a constant metallicity. Now we switch to the temperature, and we can see that this is very reminiscent of POP3 collapse, because there are no cooling except for that dust, which finally kicks in at the highest densities. We have these nice, cold, dense clumps that form, and we compare. We want to know if this is fragmentation that is indeed due to the dust, and not just the physical conditions that we've created in terms of the turbulent velocity structure. And so we rerun the collapse of this simulation without the dust. In the top, I have the density temperature progression of the simulation with dust. We can see here's that cooling phase, as this is the dust temperature itself, as the dust and gas begin to couple. And here's that same simulation run without dust. The gas stays much hotter, and it looks, at least, much less fragmented. When we run the clump finder, this is the figure that Raffaella showed earlier. This is the number of bound clumps as a function of their density. And we see, this is the dust model on top, that there is significantly more clumps in the dust version as compared to the no dust version, where there is very little fragmentation at all. So moving on, this external enrichment mechanism is very interesting because it's significantly regional dependent. We had a supernova go off at redshift 24 down here that led to no prompt star formation whatsoever. So this is the entire zoom-in region of the simulation. This is where the first supernova happened. This is where the second one that I just showed you happened. And these are zoom-ins of those two regions. And the circles represent halos that have gas in them whose dynamical times will result in collapse star formation by redshift 10 when this halo is fully assembled, and they're colored by the metallicity of the gas and sized roughly by their virial radius. In the panel of the first star, we see only basically the halo in which the star formed. So there will be no external enrichment over there. But in the other side, we see a multitude of halos at different metallicities. These all were enriched by a single event. So you could get star formation of stars with multiple metallicities that all are still tracing a single supernova. So if you're looking just at the most metal-poor stars, this could suggest that you're missing a population that also traces just a single progenitor that has higher metallicities. We can see how much of a fluke this event is simply by looking at the mean mini-halo separation as a function of redshift in the simulation. The subvolume is the line in red with the shades indicating the variation in that. And the green line here is the separation between these two halos, the POP3 star-forming halo and the halo that eventually forms the star. They actually are on a collision course eventually and will merge, which is why this goes down like this. So this is requiring a slightly below average mini-halo separation, but not by a ton. It's only about 1 sigma. So it can happen. It just may be slightly rare, okay? Now, if we want to also see when do we get any star formation from the gas phase critical metallicity that Raffaella talked about earlier of roughly 10 to the minus 3.5 Z sun, we have to run this simulation for a lot longer. And we form 10 additional POP3 stars. 3 of them are doubles. And eventually, at about redshift of 11.8, we get gas enriched to a metallicity of just under 10 to the minus 2 Z sun. And, but interestingly enough, slightly earlier than that, at redshift 12.1, we had an additional dust phase collapse happen and producing a star formation site with a metallicity of about 7 times 10 to the minus 5. Both of these were external enrichment events. I'm going to focus for now just on the gas phase collapse simulation here. This is a similar diagram showing the metallicity. We can see the wide range of metallicities out at tens and hundreds of parsecs. And as the mixing is eventually dominated by collapse, we see that the metallicity is almost constant here at just under 10 to the minus 3. That's a typo. That should be 8 times 10 to the minus 4, I apologize. Here is the density temperature diagram showing the efficient atomic line cooling here that eventually runs out of gas and the gas starts to heat back up again. We can run this collapse over again with dust too to see what it looks like if there was dust in this environment, which I think now we would expect. We don't expect this to really be dust-free. This is that same collapse run with dust, and here's a comparison of the fragmentation results. Of course, we see in the no-dust case, all the clumps really pile up at the density corresponding to the minimum temperature of the atomic cooling phase. But when you add the dust, we have clumps at a variety of higher densities up here. Of course, even when you have higher metallicity, if you're going to form low-mass stars, you're going to need to have the dust in the gas. So let's talk the last little thing. This is what the simulation, this is what our target halo looks like at the very end of the simulation at redshift 11. This is the metallicity here. You can see it's very not uniform. If we want to look very quickly at how these POP3 stars enrich this gas, how much, what we have here are plots of the, of the amount of mass and volume enriched to some minimum metallicity as a function of time and redshift. And we can see that even so we have up here 10 to the minus 6, minus 5, minus 4, and in the green is minus 3. And only a few % of the mass in the high resolution region of this simulation is enriched to a metallicity of 10 minus 3, and roughly the same amount in volume. So there's actually very little total enrichment of this gas, at least in terms of the fraction of actual gas in the simulation. If we take the volume plot and we assume spherical symmetry of the blast waves, which you've obviously seen is not true, and we look at the distance out to which the metals are traveling, we see that same plot here, and we see that after we get a few supernova, that the metals are really only getting out about a co-moving kiloparsec at most. And we can compare that again to the average mini-halo separation, and we see that there is still an overlap even down to up to metallicities of say 10 to the minus 3 with this average mini-halo separation. So I would expect to see this external enrichment process taking place early in the universe, which is something that the models by Stefania has called many years ago. So I will conclude simply by saying here's our collection of metal-enriched stars that we formed, all by this external enrichment mechanism. We, of course, know that eventually the metals will just be accreted from the IGM, and you'll get stars forming from the diffuse metals that are out there from multiple supernova. But this external enrichment mechanism, I think we've clearly shown that it happens first, and probably the lowest metallicity stars are coming from that. The next thing we intend to do is actually simulate Milky Way progenitor halos to get this in more realistic environments, and go to these websites if you want to get involved with Grackle or if you want to play with the data. Thanks.
Thank you very much, Britton. We have time for a couple of questions. All totally clear, right? Oh, I'm sorry. Right in front, Volker.
Hi, Britton. You mentioned that in your latest simulation you have a dust cooling induced event, I guess, at a metallicity of 7 times 10 to the minus 5
That's
solar.
right, yes.
So do you know what is pushing the gas to collapse in the first place? Because at those levels we won't have fine structure cooling at lower densities. So what is getting the gas to the density where dust can kick in?
So it's mostly H2 at that point. The gas, after it's been hit, gets slightly ionized, you have a higher electron fraction, you form H2, and I think it's basically all that.
Hans?
About this chemistry network and the website.
Yes.
You mentioned HD and various molecules.
That's right.
But you also mentioned helium. So I was wondering what you had in mind with how helium is involved in cooling.
Well, so helium is certainly involved in atomic cooling at very high temperatures. Currently, we don't have any helium molecules in this network. But I don't know, maybe Simon wants to add him. Sorry, Simon.
Any more questions? Going once?
I wanted to say,
Oh, yes.
this
Okay,
was,
right
wanted
there.
to say one more thing. This was a very impressive presentation.
Oh, thank you.
Give the microphone to your neighbor.
Hi, I have a question about what this dense environment will look like at redshift 0. Will it be like an L-star galaxy? Will it be, I don't know, what, a galaxy cluster? What is it going to be?
That's an excellent question that I cannot answer because I did not run it to redshift 0. I picked this halo. All I can tell you is I picked this halo because it had the maximum number of POP3 mass progenitor halos in it. I was trying to maximize the amount of metal production. But the next simulations we do, I promise, we will run at least the dark matter only simulations to redshift 0 to be able to say this is a Milky Way progenitor, this is a dwarf galaxy. I think that will be the next important step in this work.
Let's thank our speaker again.